Hey there, Year 12s. There's a question for exercise 6F, question 3b. We're wanting to sketch a sine function here with a couple of transformations that we can see. Let's read the transformation to start off with. We can see that this is implying that we are going to be moving to the right by pi on 3. There is a dilation of factor 2 from the y-axis. So it's affecting your x values. So hence your period. So let's start off with there's a lot of different ways to sketch, but this is how I normally teach students to do it. First, you identify a couple of key features like the amplitude or the range. And in this case, there is no up or down. So really the amplitude will determine the range. So you got a value of 2 because that's a vertical stretch there. Oh no, that's not a vertical stretch. What I'm talking about. The amplitude is over here. Amplitude is 1. So amplitude is 1. So that means that the sine graph, if you were to draw a rough sketch of it, it has a maximum height of 1 and a minimum height of -1. So if I drew out the graph, this is my range. My range will work between 1 and -1 because the amplitude tells us that this is 1 and this is 1. Okay, since there's no up or down, so it doesn't shift the graph up or down, it just shifts it left or right. So you're just moving it left and right, so hence the range is still going to be the same. Okay, so we've got the amplitude, we need the period. So the period is equal to 2 pi on n, which in this case is the dilation factor. And since it's a dilation of factor half, I just realized I made a mistake there. That should have been factor of half since that's a 2. So then that's 2 pi times half, which gives you pi. So we know that in order to do one cycle of this graph, that's going to end up being a distance of pi. Okay. And then now, how do I normally sketch a sine graph? Well, first you just need to know the shape. So we know the shape kind of looks like this. And I always choose one point, which is the starting point. So this is called your starting point. And we know that the graph, okay, the starting point would have been at 0, 0 for a sine graph, but because it's moved to the right by pi on 3, so you can sort of visualize it as I'm moving this to the right by pi on 3. So now the graph is starting at pi on 3, 0 instead, which is over here. Okay, so in other words, what I'm saying is that the graph shifts across to the right, and I know that's now pi on 3, and that's your starting point, which is here. We know there's a maximum of 1 and a -1, and then from here, to sketch the graph, because they told us that there's a domain, x is an element of 0 to 2 pi, so there is obviously a starting point at 0, and then it finishes off at 2 pi somewhere. Okay, so I don't know how many cycles I'm going to end up. It could be like this, but I just know at some point when I get to 2 pi, it should stop. So how do we then sketch this? Well, the way I taught in class is that I asked you guys to find the quarter cycles, because every quarter the graph reaches, so this is a quarter of this graph, it reaches its maximum. The next quarter reaches the middle again, and then the next quarter reaches the minimum. So you can see if I split them into quarters, that graph, the sine graph, is split up into intervals. So that's the first quarter, the second quarter, third quarter, fourth quarter, and then it's easy to kind of visualize what will happen to the graph. So to figure out how much of a distance it is to get from this to the quarter cycle, well, we need to then find the quarter of a period, because we know the period is how long it takes to do one cycle. Then I only need a quarter of the cycle, meaning I only need it from the starting point to the maximum. So I want to know how far that is. So to find the quarter of a period, well, since the period is pi, then a quarter of a period is equal to then pi divided by 4. All right. So what I know is that in this graph here, if I want to know how long before it takes to reach to the maximum, well, it needs to go across by an extra pi on 4. And we can see here that adding pi on 3 and pi on 4 doesn't make it easy because the denominators are different. So I'm going to change them to the lowest common denominator. So pi on 3 plus pi on 4, well, I know the lowest common multiple is 12. So if I change them into 12ths, it makes it easier to count. So that means pi on 3 is the same thing as saying 4 pi on 12. And then pi on 4 is the same thing as saying 3 pi on 12. So now what we can see is that instead of saying pi on 3, okay, so instead of pi on 3, I'm going to change this now to saying that is where 4 pi on 12 is. Okay, and if you think about it, you want to make it easier when you're sketching this graph. Doing a scale of pi on 12s will make our lives easier. So for example, if I just did this, I'm just going to do a little scale so we can see. Let's call that 1 pi on 12, 2 pi on 12, 3 pi on 12, then 4 pi on 12, and then 5 pi on 12, and then 6 pi. So you get the idea. I'm just going to do 6, 7, 8, 9, 10, 11, 12. Now that's 12 pi on 12, which is equivalent to 1 pi. Remember, we need to keep going until we get to 2 pi. So I'm just going to follow that pattern. And that's 13, 14. Sorry, that's not to scale. Yeah? This is 14, 15. It looks like I have to continue. So 16's here, 17's there, 18's here, 19's here, 20's here, 21 is here. And that's what, 22, 23. And I finish at 24 pi on 12 here, which is equivalent to 2 pi, right? So now that I've got that sort of scale, and actually, I just realized I miscounted, didn't I? Because there's a little half node here. How do I go back? I can't be bothered fixing all this. I'll just do it again. All right. I just realized I missed that little detail here. So this should have been 1. That should have been 2, 3, 4, 5, 6, 7. So everything's just back by 1. All right. So it's 1 pi on 12, 2 pi on 12. I just can't be bothered writing them all, but you get the idea, right? So from here, 8, 9, 10, 11, 12, 13, 14. So it means 12 pi on 12 was here, so that's equal to pi there. 14, 15, 16, 17, 18. And I'm just going to do it all again. 19, 20, 21, 22. So 19, 20, 21, 22, 23, 24. All right, and that's 24 pi on 12, which is equivalent to 2 pi. Great. Okay, so now I've done that in terms of scales. Can you see the benefit is that I said pi on 3 was the starting point, right? Which is at 4 pi on 12. So when you look at it, this is your starting point. So I'm going to put a starting point. And how many do you need to get to the maximum? We said a quarter cycle, right? And a quarter cycle was pi on 4, which really is just adding another 3 pi on 12. So when I count it, it's easy. You're just going 1, 2, 3. So you must be at 7 pi on 12 in order to have a maximum, which it goes like that. You can see that? Plus another 3, that means it gets down to 10. So it comes down like this. Plus another 3, so 10 plus 3 is 13. So it should go to the minimum. So it goes all the way to the bottom like that. And then plus another 3 is 16, so it gets back to the center. And then 16 plus 3 again gives you 19, so maximum is 1 again, so it comes back up. And then it goes, 19 plus 3 is 12, so it goes down, oh sorry, not 12, 22, comes down to this point. 22 plus another 3 should then be at 25 pi on 12, which is down this way. So that means that it cuts off just before it reaches the bottom. So you can almost predict this is going to be your endpoint there. So this is the endpoint where it's at 2 pi, and we don't know what the y value is yet. But we know it's not the minimum. Okay, whereas this one, we know at 13 pi on 12, it should have been at -1. Yeah, and same thing up here. We knew the maximum was a 7 pi. On 12, it should have been at 1. Okay? And the benefit of doing the scale like that is that you can even work backwards. So if you know 4, you subtract 3, going backwards, it will reach the minimum. So it'll reach the minimum at 1.5, or 1 pi on 12, sorry. And then it'll slightly, before it gets to 0, it goes back up. So right now, I know that x is 0, I just don't know what the endpoint at 0 is. But you can get a shape of the graph already just by looking at that. And all I did was I found the starting point. So how did I find the starting point? I knew the shape of a sine graph, and I read the transformation and said moved to the right by pi on 3. So I knew the starting point was at pi on 3, 0. So I knew this was the starting point. Then to find the maximum and the middles and the minimum, I just needed to find the quarter cycles because the sine graph is broken up into quarters. Right? So it reaches the maximum in the first quarter, second quarter it reaches middle, third quarter reaches bottom, and the fourth quarter reaches back to the middle again. So all I needed was the quarter cycles. So here's my quarter cycles, a quarter of the period. And then I changed it so that denominator is all the same, so it's easy to count. So you're starting at 4 and you're adding on 3, and that's all I did. I started off at 4. I added on 3 to get to 7, and so I know that was the maximum. And I added another 3. That's how I knew it went back to the middle. And then I added another 3. And that's how I knew it went to the minimum. And then I just followed that pattern to get all the maximum and minimums there. And conveniently, because this doesn't shift the graph up or down, I also happen to have the x-intercepts as well. So I've got all the x-intercepts there. This is at 4 pi on 12, which can be simplified to pi on 3. This one is 10 pi on 12, which technically can be simplified to 5 pi on... Wait, did I do it right? 5 pi on 6. Yeah. And then same thing with the 10 pi. Wait, no. What's that one? 16 pi. 16 pi on 12, which divided by 4 is 4 pi on 3. Okay. And then to find endpoints, to finally finish off the sketching, we got to find the endpoints. Sorry, this is 22 pi on 12, which is the same thing as 11 pi on 6. All right, and then to find the endpoints, we know that the starting point was when x is equal to 0, and the other one is when x equals to 2 pi. So you sub that back into the equation. So y, or f, is f of 0 is equal to sine of 2 times 0 minus pi on 3. Use a calculator if you're not good with your exact values at this point. And same thing with this one. This is sine of 2 times 2 pi minus pi on 3. So you can use your exact values, or you can use a calculator to solve the endpoints there. Another way of thinking about this is actually asking you to find the sine of negative 2 pi on 3. And this one is to ask you to find sine of, what's that? 3, 6, 5 pi on 3, so 10 pi on 3. Okay? And if you would do it by hand, you can kind of visualize where negative 2 pi on 3 is, or if you rewrite it, that's the same thing as writing negative pi plus pi on 3. Yeah, because you're like at negative 3 and you're just missing, if you add another 1 pi, then you'll get negative 2. Right, so this is all exact values practice. So if you're not understanding what I'm doing here, that means you got to go back and make sure that you can do symmetry properties on 6e, I think it was. And the same thing with this one. This is sine of, and you can rewrite that as 3 pi, which is 9 pi on 3, plus an extra pi on 3. So if you had to visualize that on a unit circle, negative pi, well, this is 0, negative pi is over here. And you are now adding pi on 3, and because you're adding, you're going anti-clockwise, so you're back down here. So sine will be negative in that region, so I know the answer has to be negative of sine of pi on 3. Sine of pi on 3 gives you this height here, and sine of pi on 3 is negative root 3, 2 there. And then same thing with this one, 3 pi is also in that same region. If you think about it, that's 1 pi, 2 pi's, and 3 pi. So 3 pi also happens to be in the same spot. So 3 pi is here, and you're adding an extra pi on 3, so it happens to be the same value. So it's negative root 3 on 2. So if I were to answer the question here, this must be at 0, negative root 3 on 2. And this is at 2 pi, negative root 3 on 2. And that is your graph. So you've got the endpoints, you've got your range, negative 1 to 1, and you've got your x-axis intercepts as well. All right, let me know if that makes sense. But for all graphs, no matter which graph I get, whether it's 6F or 6G or 6H, I follow pretty much the same technique. Some of the questions you may have to actually find the x-intercepts, but you don't have to when there isn't any moving up or down. So if there's no vertical translations, and then it doesn't affect the x-intercepts, it makes it easy to calculate as you're sketching. All right, but that's what I do first. I normally just visualize what does the graph normally look like, figure out the starting point based on the transformations, and then I find the period and I work out the quarter periods for it. The amplitude helps you to figure out where the maximum and the minimum is and where the middle is. That's what it does. Okay. Let me know if there's more practice you'd like, but yeah, that's how I normally teach. I think it's the easiest way, but it is the tedious way to do it. It's the easiest way to get. It's the most tedious to sketch, because I'm pretty sure this is going on between 15 to 20 minutes of my explanations. Obviously, if I did it, it's a bit faster, but when you do it for the first time, it may be longer as you're sort of getting your head around it. Okay.